Light years, measuring distance in time. Right now, wherever you are, light is touching you. It is arriving from the lamp beside your bed, or from the glow of a screen, or from the streetlight filtering through your window. It reaches you almost instantly. You flip a switch and the room fills. You open a curtain and the morning arrives. Light, in our daily experience, feels immediate. It feels like something that simply is, that needs no time to travel, no permission to appear. But light is not instantaneous. It moves, it travels, it crosses distance the way anything else crosses distance, except that it does so faster than anything else in the known universe. Light moves at just under 300,000 kilometers every single second. That is roughly 186,000 miles in the same heartbeat of time. Nothing we have ever discovered in nature moves faster. Nothing even comes close. And yet, even at that extraordinary speed, light takes time to get from one place to another. The light from the lamp beside you has traveled only a few feet, and it arrived in less than a billionth of a second. But the light from the sun has a longer journey. It crosses 93 million miles of empty space before it reaches your face, and that crossing takes a little more than 8 minutes. When you look at the sun on a quiet afternoon, you are not seeing it as it is right now. You are seeing it as it was 8 minutes ago. You are looking, however briefly, into the past. This is where something remarkable begins to unfold. This is where distance and time start to fold into one another, where the ordinary act of seeing becomes something almost philosophical. Because in the universe, measuring how far away something is also means measuring how long ago its light left home. The two questions, how far and how long ago, turn out to be the same question, expressed in different words. And that is what a light year is, not a unit of time, despite its name. A light year is a unit of distance. It is the distance that light travels in one full year, moving at its constant and unwavering speed through the vacuum of space. One light year is approximately 5.88 trillion miles. That is a 5 followed by 12 zeros. It is a number so large that it resists the imagination, a distance so vast that no human metaphor can quite hold it. And yet, in the grand architecture of the cosmos, a single light year is a relatively modest stretch. There are objects in the sky whose light has been traveling for billions of years, crossing billions of light years to arrive here tonight at your eyes. Tonight we are going to follow light on its journey. We are going to trace the paths it takes from the nearest stars to the farthest galaxies ever observed. We are going to walk, step by step, through the story of how humans learned to measure these impossible distances and what it truly means that every time we look into the night sky, we are looking backward through time. There is no rush. The distances are vast. The light has been patient for billions of years, and so can we. Let yourself settle into that idea for a moment. Wherever you are right now, you are surrounded by light that has traveled different distances to reach you. The glow of the lamp beside you has crossed a few feet. The light reflecting off the walls has bounced from surface to surface in millionths of a second. But if you were to look out a window and see a star, that light has crossed trillions of miles through the emptiest, coldest space imaginable, and it has been traveling longer than you have been alive. It arrives at your eye as a single, tiny point of brightness, and in that point is encoded a story of distance, a story of time, a story of the universe itself, patiently telling its history to anyone willing to look up and listen. To understand the light year, it helps to begin with light itself, and with the long history of people trying to figure out what it is and how fast it moves. For most of human history, people assumed that light traveled instantaneously. When a candle was lit, the room was bright. There seemed to be no delay, no gap between the moment of ignition and the moment of illumination. The great philosopher Aristotle believed that light was not something that moved at all, but rather a state that the transparent medium simply entered. Darkness was normal. Light was an alteration, and that alteration happened everywhere at once. Even Galileo, centuries later, was not entirely sure whether light had a speed or not. In the early 17th century, he designed an experiment to find out. He placed himself on one hilltop and an assistant on another, each holding a covered lantern. The idea was simple. Galileo would uncover his lantern, and when his assistant saw the flash across the valley, the assistant would uncover his own. By measuring the time between the two flashes, Galileo hoped to calculate the speed of light. But the experiment failed. Human reflexes were far too slow. The distance was far too short. Whatever speed light possessed, it was beyond the reach of hilltop signals and human hands. Galileo could only conclude that if light was not instantaneous, it was at least extraordinarily fast, faster than anything he could measure. It would take another several decades and a far more creative approach before anyone managed to catch light in motion. In 1676, a Danish astronomer named Ole Rømer was working at the Royal Observatory in Paris. He was not trying to measure the speed of light. He was studying something else entirely, something that seemed unrelated. He was carefully recording the eclipses of Io, one of the 4 large moons of Jupiter, as Io disappeared behind the giant planet and then re-emerged on the other side. Rømer had been timing these eclipses over many months, expecting them to occur at perfectly regular intervals. Io circled Jupiter every 1.769 Earth days, and the eclipses should have been as predictable as clockwork, but they were not. When Earth, in its own orbit around the Sun, was moving closer to Jupiter, the eclipses seemed to arrive a little early, a few minutes ahead of schedule. When Earth was moving away from Jupiter, they arrived a little late. The discrepancy was small, about 22 minutes over the course of half a year, but it was consistent and unmistakable. Rømer understood what this meant. The light from Jupiter's moon was not reaching Earth instantaneously. When Earth was farther from Jupiter, the light had a greater distance to cover, and it took more time to arrive. When Earth was closer, the distance was shorter and the light arrived sooner. Light, he concluded, had a finite speed. It traveled through space at a measurable rate, and that rate could be calculated from the discrepancy in the eclipse timings. From his observations, Rømer estimated that light needed about 22 minutes to cross the entire diameter of Earth's orbit around the Sun. His number was somewhat too high. The actual figure is closer to 16.5 minutes, but the principle was correct, and it changed everything. For the first time in human history, a person had demonstrated that light was not infinite. It traveled. It took time. And if it took time, then the light arriving from distant objects was not showing us the present. It was showing us the past. This idea did not gain immediate acceptance. Giovanni Cassini, the director of the Paris Observatory where Rømer worked, never fully embraced it. Many astronomers of the time preferred to believe that light was instantaneous, as it had always seemed. It would take more than 50 years before the English astronomer James Bradley provided independent confirmation, using a completely different method. Bradley was observing stars carefully over the course of a year, tracking their positions with extreme precision, when he noticed something peculiar. The apparent positions of stars shifted very slightly depending on the time of year, tracing tiny ellipses in the sky over a 12-month cycle. This phenomenon, called stellar aberration, had nothing to do with the stars themselves. It was caused by the combination of Earth's orbital motion and the finite speed of incoming starlight, in much the same way that raindrops, which fall straight down in still air, appear to slant toward you when you walk through a storm. The faster you walk, the more they seem to tilt. Bradley realized that the slight tilt of starlight told him the ratio of Earth's speed to the speed of light, and from this he calculated that light took about 8 minutes and 13 seconds to travel from the Sun to Earth. His value was remarkably close to what we accept today. Two independent methods, decades apart, using entirely different observations, had arrived at nearly the same answer. Light traveled at a finite speed, and that speed was approximately 300,000 kilometers per second. The confirmation was quiet and gradual, but its implications were vast. If light took time to travel, then everything we saw in the sky was a delayed image. The stars were not showing us what they looked like right now. They were showing us what they looked like when their light departed, however many years ago that had been. The night sky, in other words, was not a window to the present. It was a gallery of the past, with each star hanging at a different depth in time. In the centuries that followed Rømer and Bradley, the measurement of light speed was refined again and again. In 1849, the French physicist Hippolyte Fize devised a clever terrestrial experiment using a rapidly spinning toothed wheel and a mirror placed several kilometers away. Light was sent through a gap in the spinning wheel, reflected off the distant mirror, and returned. If the wheel was spinning at just the right speed, the returning light would be blocked by the next tooth. By adjusting the rotation rate, Fize could calculate the travel time and thus the speed. His result, about 315,000 kilometers per second, was impressively close. A few years later, his colleague Léon Foucault improved the apparatus using a rotating mirror and arrived at a value even closer to the modern one. By the 20th century, Albert Einstein had placed the speed of light at the center of a new understanding of the universe. In his special theory of relativity, published in 1905, Einstein proposed that the speed of light in a vacuum is not just very fast. It is a fundamental constant of nature, the same for all observers regardless of their motion. Nothing with mass can ever reach it. Nothing can exceed it. It is the absolute speed limit of the cosmos, woven into the very structure of space and time. And from this single, elegant postulate flowed some of the most profound insights in the history of science. That time passes differently for objects in motion, that mass and energy are interchangeable, that the geometry of the universe is not what our intuition would suggest. The speed of light was eventually defined with extraordinary precision. In 1983, the international scientific community fixed it at exactly 299,792,458 meters per second. This number is no longer a measurement. It is a definition. The meter itself is now defined in terms of the speed of light, as the distance light travels in a vacuum in 299,792,458th of a second. Light's speed is so fundamental, so unvarying, that it has become the ruler by which we measure everything else. So light has speed, it has a journey, and when that journey is long enough, the time it takes becomes deeply significant. The sun is 8 light minutes away. The light warming your skin right now left the surface of a star over 8 minutes ago. If the sun were to suddenly vanish at this very moment, you would not know for 8 more minutes. You would continue to feel its warmth, see its light, live under its glow for 8 more minutes before the news arrived. The moon is much closer. Reflected sunlight from the moon reaches you in about 1¼ seconds. That is the distance of a single heartbeat. When astronauts on the Apollo missions spoke to mission control in Houston, their words took about 1.3 seconds to travel from the lunar surface to Earth. That brief delay, barely noticeable in conversation, was the distance between two worlds rendered in time. The other planets in our solar system are farther still, and the delays grow accordingly. Mars, depending on where it sits in its orbit, is between 4 and 24 light minutes away. When NASA engineers send a command to a rover on the Martian surface, they must wait at least 8 minutes for the signal to arrive and the confirmation to return. They cannot steer the rover in real time. The speed of light, fast as it is, imposes a delay that cannot be overcome. Jupiter is about 35 to 52 light minutes distant, Saturn roughly 67 to 89 light minutes. Neptune, the most distant major planet, lies about 4 light hours away. A message sent at the speed of light from Earth to Neptune would take longer than a transatlantic flight to arrive. The edge of our solar system, at the outermost boundary of the Oort cloud, a vast and ghostly shell of dormant comets, is about 1½ light years away. Even a beam of light, the fastest thing in existence, takes more than a year to cross from the Sun to the outer boundary of our own solar neighborhood. A spacecraft traveling at typical speeds would need tens of thousands of years. Beyond the Oort cloud lies the interstellar void. The nearest star to our Sun is called Proxima Centauri, a small, dim red dwarf star, part of a triple star system in the southern constellation of Centaurus. Proxima Centauri sits about 4.24 light years from Earth. The light you see from it tonight, if you are in the southern hemisphere and know where to look, left that star more than 4 years ago. Whatever is happening there right now, whatever storms rage on its surface, or whatever planets orbit quietly in its faint red glow, we will not learn about it until 4 years from now, when the light carrying that information finally completes the crossing. If you were to board a spacecraft traveling at the speed of the fastest probe humanity has ever launched, roughly 40,000 miles per hour, it would take you approximately 70,000 years to reach Proxima Centauri. 70,000 years. That is longer than the entire span of recorded human civilization, longer than the age of the cave paintings at Lascaux, longer than the distance between the last ice age and this moment. And that is the distance to our nearest neighbor among the stars. In the language of the cosmos, It is practically next door. Look a little farther and you find Sirius, the brightest star in the night sky, about 8.6 light-years away. The light from Sirius that reaches you tonight left that star when you were perhaps 8 years old. Vega, one of the brightest stars in the northern sky, is about 25 light-years away. Its light has been traveling since before you were born. Polaris, the North Star, is roughly 430 light-years distant. The light you see from it tonight left that star when Galileo was still alive, when Shakespeare was writing plays, when the first permanent European settlements were being established in North America. And those are just the stars you can see with the naked eye. Betelgeuse, the great red shoulder of Orion, sits about 650 light-years away. Its light departed during the Middle Ages, when cathedrals were being built across Europe and the Mongol Empire was reshaping the map of Asia. Deneb, the brilliant star at the tail of Cygnus the Swan, is roughly 2,600 light-years distant. The photons arriving from Deneb tonight began their journey when the ancient Greeks were building the Parthenon. By the time those photons reach your eyes, the civilization that first named the constellation they belong to has risen, transformed, and been absorbed into history many times over. The star Eta Carinae, a massive and unstable star buried within a beautiful nebula in the southern sky, is about 7,500 light-years away. Its light has been traveling since the earliest known civilizations in Mesopotamia were learning to write. If Eta Carinae were to explode tomorrow in a spectacular supernova, as many astronomers believe it eventually will, we would not see the explosion for another 7,500 years. The news of its death would travel at the speed of light, and even that ultimate speed would need millennia to cross the distance. Now the distances begin to stretch in earnest. Our galaxy, the Milky Way, is a vast spiraling collection of stars, gas, dust, and dark matter, held together by gravity and slowly rotating over hundreds of millions of years. It contains somewhere between 100 billion and 400 billion stars. From one edge to the other, it stretches roughly 100,000 light-years. That means a beam of light, traveling at the fastest speed the universe allows, would need 100,000 years to cross from one side of our galaxy to the other. Light that left one side of the Milky Way when early humans were first learning to paint on cave walls has still not reached the other side. Our sun sits about 27,000 light-years from the galactic center. The light from those central stars, the dense and luminous heart of the Milky Way, has been traveling since before the last ice age, before the domestication of animals, before the invention of agriculture. It set out on its journey when woolly mammoths still roamed the plains of Eurasia, when the world was colder and wilder, and it has been crossing the dark, quiet space between stars ever since, patient and unchanged, until it reached your eyes tonight. Beyond our galaxy, the distances grow larger still. The nearest major galaxy to our own is the Andromeda Galaxy, a beautiful spiral of approximately 1 trillion stars, about 2.5 million light-years from Earth. When you look at Andromeda on a clear dark night, and it is visible to the naked eye as a faint, elongated smudge of light in the constellation of the same name, you are seeing light that left that galaxy 2.5 million years ago. You are seeing Andromeda as it was when the earliest members of our genus, Homo, were beginning to emerge on the African savanna. The galaxy you observe is a portrait from the deep past, captured in photons that have been faithfully crossing the void between our two galaxies ever since. And Andromeda is close, by cosmic standards. It is part of our local group, a small cluster of galaxies bound together by gravity. There are galaxies billions of light-years away from us, galaxies whose light has been traveling since before Earth existed, since before our sun ignited, since the universe itself was young and still cooling from its violent beginning. Every photon that reaches us from those distances is an artifact, a messenger carrying news from an era that no human has ever witnessed, that no living thing on Earth has ever known. Beyond the local group, the distances expand into a hierarchy of structures that stretches the imagination. The Virgo cluster, a massive collection of over 1,000 galaxies, lies about 54 million light-years away. The light from Virgo that astronomers study today left those galaxies when dinosaurs had already been extinct for 10 million years, and the ancestors of modern horses were the size of small dogs. The Coma Cluster, another great gathering of galaxies, is roughly 320 million light-years distant. Its light departed when the first amphibians were beginning to crawl onto land, when the Earth was a warmer, wetter, stranger place than anything we would recognize. And beyond the clusters lie the superclusters, and beyond those, the great cosmic web, an immense network of filaments and walls of galaxies separated by vast, nearly empty voids hundreds of millions of light-years across. The observable universe, taken in its entirety, resembles something like a sponge or a neural network, with matter concentrated along thin threads and sheets, and enormous dark spaces in between where almost nothing exists. This structure was not imposed from outside. It grew from the tiny fluctuations in the distribution of matter in the very early universe, amplified by gravity over billions of years into the grand architecture we observe today. So how do astronomers measure these extraordinary distances? How do they determine that one star is 4 light-years away and another is 4,000, that one galaxy is 2 million light-years away and another is 12 billion? The answer is not simple. It is a story of patience and ingenuity, a series of increasingly clever methods, each one building on the one before it like rungs of a ladder reaching outward from Earth into the deepest reaches of the cosmos. Scientists call it the cosmic distance ladder, and it is one of the great achievements of human thought. The first rung is the oldest and most intuitive method. It is called parallax, and it works on the same principle you experience when you hold your thumb in front of your face and close one eye and then the other. Your thumb appears to shift against the background. That apparent shift is parallax. The amount it shifts depends on the distance. The closer the object, the greater the shift. The farther the object, the smaller the shift. Astronomers use the same principle, but instead of two eyes separated by a few inches, they use Earth's orbit around the Sun as their baseline. In January, Earth is on one side of the Sun. In July, it is on the opposite side, roughly 186 million miles from where it started. By observing a nearby star from these two positions, 6 months apart, and measuring how much it appears to shift against the background of more distant stars, astronomers can calculate its distance using simple geometry. The parsec, another unit used by professional astronomers, is actually defined by this method. 1 parsec is the distance at which a star would show a parallax angle of 1 arcsecond, and it equals about 3.26 light-years. This method was first used successfully in 1838 by the German astronomer Friedrich Bessel. He targeted a star called 61 Cygni in the constellation of the Swan, and after painstaking observations with a specially designed instrument called a heliometer, he determined that the star was approximately 10.3 light-years from Earth. It was the first time anyone had measured the distance to a star beyond the Sun. The number was staggering. Even the nearest stars were trillions of miles away, distances so large that a new unit of measurement was necessary simply to express them in comprehensible terms. But parallax has a natural limit. The farther away a star is, the smaller its apparent shift becomes, and eventually the shift is too tiny to measure, even with the most precise instruments. From the ground, parallax is reliable for stars within a few hundred light-years. Space telescopes have extended this range dramatically. The European Space Agency's Hipparcos satellite, launched in 1989, measured the positions and distances of over 100,000 stars with far greater accuracy than any ground-based observatory could achieve. And its successor, the Gaia spacecraft, launched in 2013, has gone even further. Gaia is currently mapping the positions, distances, and motions of nearly 2 billion stars in our galaxy, creating the most detailed three-dimensional map of the Milky Way ever constructed. It measures parallaxes with a precision of millionths of an arcsecond, allowing accurate distances to be determined for stars thousands of light-years away. But even Gaia's extraordinary capabilities cannot reach across the full extent of the universe. For truly distant objects, galaxies millions or billions of light-years away, parallax is useless. The shift is simply too small, far smaller than any instrument can detect. Astronomers needed a different kind of rung on the cosmic distance ladder, a method that could work across vastly greater distances. They found one in a remarkable type of star called a Cepheid variable. These are stars that pulsate, expanding and contracting in a slow, steady rhythm, growing brighter and dimmer like a cosmic heartbeat. In the early 20th century, a Harvard astronomer named Henrietta Swan Leavitt made a discovery that would change the course of astronomy forever. Leavitt was one of a group of women known as the Harvard computers, employed to catalog and analyze photographic plates of the night sky at a time when women were not permitted to operate the observatory's telescopes. Despite this restriction, or perhaps because of the meticulous attention her cataloging work demanded, Leavitt noticed something no one else had seen. While studying photographic plates of stars in the small Magellanic Cloud, a small satellite galaxy visible from the southern hemisphere, she found a pattern among the Cepheid variable stars. Those that pulsated more slowly, with longer periods between their brightenings and dimmings, were intrinsically more luminous than those that pulsated quickly. The relationship was precise and reliable. If you measured a Cepheid's period, you could predict its true brightness. Leavitt published her findings in 1912, and though she received little recognition during her lifetime, her discovery, now called the Leavitt Law, became one of the most important tools in all of observational astronomy. This was an extraordinary insight, and its implications were enormous. If you know how bright a star truly is, its intrinsic luminosity, and you measure how bright it appears from Earth, the difference tells you how far away it is. It is the same principle you intuitively understand with a candle. A candle at arm's length looks bright. The same candle a mile away looks faint. The dimmer it appears, the farther it must be. Cepheid variables became what astronomers call standard candles, objects of known brightness that can be used to gauge the distance to their surroundings. Using Cepheids, astronomers pushed the distance ladder outward, first to the edges of our galaxy, then far beyond. It was Cepheid measurements that allowed Edwin Hubble, in the 1920s, to prove that the fuzzy patches of light called spiral nebulae were not clouds of gas inside the Milky Way, as most astronomers had assumed, but entirely separate galaxies, vast collections of stars millions of light years from our own. Hubble used the 100-inch Hooker telescope on Mount Wilson in California, at that time the largest telescope in the world, to identify individual Cepheid stars in the Andromeda Nebula, by measuring their periods and apparent brightness. He calculated that Andromeda was nearly 1 million light-years away, far beyond the boundaries of the Milky Way. In a single set of observations, the known size of the universe expanded by a factor of thousands. The Milky Way went from being the entire cosmos to being one island among billions. But Hubble's most famous discovery was still to come. As he measured the distances to more and more galaxies and compared those distances with measurements of how fast the galaxies were moving, he noticed a startling pattern. Almost every galaxy was moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was not static, as nearly everyone, including Einstein, had assumed. It was expanding. Every galaxy was being carried away from every other galaxy by the stretching of space itself, like raisins in a loaf of bread that is rising in the oven. This relationship between distance and recession speed became known as Hubble's law, and it implied something extraordinary about the history of the universe. If everything is moving apart now, then everything must have been closer together in the past. Run the expansion backward far enough, and you arrive at a moment when all the matter and energy in the universe was compressed into an unimaginably hot, dense state, the Big Bang. For even greater distances, beyond the reach of individual Cepheids, astronomers turn to an even brighter standard candle. A particular type of stellar explosion, called a Type Ia supernova, occurs when a dense, dead star called a white dwarf accumulates matter from a companion star until it reaches a critical mass and detonates in a thermonuclear explosion of remarkable consistency. Because these explosions occur at nearly the same mass every time, they produce nearly the same peak brightness every time, making them visible across billions of light years and usable as cosmic yardsticks. It was observations of these supernovae in the late 1990s that revealed one of the most startling discoveries in modern science. Two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using Type Ia supernovae to measure the expansion rate of the universe at different points in its history. They expected to find that the expansion was slowing down, gradually decelerating as gravity pulled on all the matter in the cosmos. Instead, they found the opposite. The universe is not only expanding, it is accelerating. The most distant supernovae appeared dimmer than expected, meaning they were farther away than a universe expanding at a constant rate would predict. Something was pushing the expansion to go faster with time. Scientists named this mysterious force dark energy, and despite decades of investigation, its nature remains one of the deepest unsolved problems in physics. Whatever dark energy is, it constitutes roughly 68% of the total energy content of the universe. Ordinary matter, the atoms that make up stars and planets and human bodies, accounts for less than 5%. Dark matter, another mysterious substance that exerts gravitational influence but emits no light, makes up about 27%. The universe, it turns out, is mostly composed of things we do not understand, and it was the study of light traveling across billions of light years that revealed this humbling truth. There is something else that happens to light as it travels across these immense distances, something that reveals a deep truth about the nature of the universe itself. Light that has been traveling for billions of years does not arrive the same color it started. Its wavelengths are longer than when it was first emitted. Blue light becomes red. Ultraviolet shifts into the visible range. Visible light slides into the infrared. Astronomers call this cosmological redshift. Redshift occurs because space itself is expanding. The universe is not a fixed container in which galaxies float like boats on a still lake. The fabric of space is stretching gently and continuously, and as it stretches, the light traveling through it stretches too. Imagine drawing two dots on the surface of a balloon and then slowly inflating it. The dots move apart, not because they are traveling across the surface, but because the surface itself is growing between them. Light waves riding through expanding space experience the same effect. Their wavelengths elongate, they redden, and they carry, written in their altered color, a record of how much the universe expanded during their long journey. This means that the most distant galaxies we can observe appear deeply reddened. Their light, which may have started as bright ultraviolet or blue billions of years ago, has been stretched across the electromagnetic spectrum during its voyage through expanding space. By the time it reaches our telescopes, it arrives as faint infrared radiation, barely perceptible, carrying ancient information in its tired, elongated wavelength. The James Webb Space Telescope was designed precisely to capture this kind of light. Its golden, segmented mirror, over 6 meters across, collects infrared photons with extraordinary sensitivity. When Webb turned toward a small, seemingly empty patch of sky in 2022, holding its gaze for just 12.5 hours, it produced an image that redefined our view of cosmic history. Thousands of galaxies appeared in a sliver of sky no larger than a grain of sand held at arm's length. Some of those galaxies existed when the universe was less than 1 billion years old. Their light had traveled more than 13 billion years to reach the telescope's sensors. The most distant galaxy, yet confirmed by Webb, a small, unusually bright object called JADS GSZ140, appears to us as it existed just 290 million years after the Big Bang, when the cosmos was barely 2% of its current age. Think about what that means, quietly, without rushing. The light captured in that image had been traveling since before the Earth existed, before the sun formed from a collapsing cloud of gas and dust, before most of the stars you see in the sky tonight were born. That light began its journey when the universe was young and hot and turbulent, when galaxies were still assembling themselves from clouds of primordial hydrogen, when the cosmos looked nothing like the structured, star-filled, galaxy-laced expanse we observe today. When we look at those ancient galaxies, we are not just seeing far away, we are seeing far ago. We are seeing the universe in its infancy, when it was less than 2% of its current age, when the first generation of stars was just beginning to forge the heavy elements that would eventually become planets, oceans, and the chemistry of life. Every atom of iron in your blood, every atom of calcium in your bones, was created inside a star that exploded billions of years ago. The light from those earliest stellar generations is what Webb's instruments are gathering. In a very real sense, Webb is looking back at the forges where the raw material of our bodies was first made. And yet those photons arrived. They survived the entire unfolding history of the universe, traveling silently through the expanding void, passing through regions of space where galaxies would eventually form and then grow old, passing through the darkness between galaxy clusters, through the great cosmic voids where almost nothing exists at all, until they touched a golden mirror orbiting a small rocky planet around an ordinary star in an ordinary spiral galaxy. And they were gathered and translated and decoded by a species that had existed for less than an eye blink of cosmic time. There is a question that often arises when people first encounter these distances, and it is a beautiful question, one worth sitting with. If the universe is 13.8 billion years old, how can we see objects that are 46 billion light years away? Surely light could not have traveled a distance greater than the age of the universe would seem to allow. It seems, on the surface, like a contradiction. The answer lies in the expansion itself. While light was traveling toward us, the space behind it was stretching. The galaxy that emitted its light 13.8 billion years ago was not 13.8 billion light years away when the light left. It was much closer. But during the billions of years that the light was in transit, the continuous expansion of space carried that galaxy farther and farther from us. Today, that galaxy sits roughly 46 billion light years away. The light travel distance and the actual current distance are different things entirely, because the road itself was lengthening the entire time the light was walking along it. The observable universe, the portion of the cosmos from which light has had time to reach us since the beginning, has a diameter of about 93 billion light years. It contains an estimated 2 trillion galaxies, each one home to billions or hundreds of billions of stars. And beyond the edge of what we can observe, the universe almost certainly continues. It may be vastly larger than what is visible. It may, in fact, be infinite. We do not know, and we may never know, because the light from those more distant regions has not yet had time to arrive. It is still on its way. It is still crossing the expanding distance between there and here, and it will continue crossing that distance for eons to come. Somewhere out there, right now, photons are traveling through space that will not reach Earth for another billion years. Another 10 billion years. They carry images of galaxies no human has ever seen, no telescope has ever captured, no mind has ever imagined. They are faithful messengers on an unimaginably long journey, and they are infinitely patient. There is something deeply calming about this thought. The universe does not rush. Light does not hurry. A photon leaving a distant star does not worry about whether it will ever be seen. It simply travels at the only speed it knows through whatever space lies ahead of it for however long the journey takes. It does not tire. It does not age. According to the strange mathematics of relativity, a photon experiences no passage of time at all. From the photon's perspective, if we can speak of such a thing, its departure and its arrival are the same moment. The billions of years of travel happen only for those who wait and watch. For the light itself, the entire crossing is instantaneous. It is the observers who experience the distance as time. And so, in a way, every photon that reaches your eye carries two truths at once. It tells you how far away its source is, and it tells you how long ago that source was shining. Distance and history, folded together, delivered as a single point of light on a dark night. The light year captures this duality perfectly. It is named for time, but measures space. It is a unit of distance defined by duration. It is the universe's own way of reminding us that here and there, now and then, are not as separate as they seem. When you look at the night sky, you are not seeing a single moment. You are seeing many different moments in time, all arriving simultaneously, layered on top of one another like pages in a book that has been opened all at once. The moon shows you a moment from 1.3 seconds ago. The planets show you minutes to hours in the past. The familiar stars of Orion show you centuries in the past. The faint blur of Andromeda shows you millions of years in the past. Each point of light is a different chapter in the history of the universe, and they are all arriving at the same instant, overlapping, accumulating, composing a mosaic of time itself. No other experience available to a human being compresses so much time into a single glance. A walk through a forest might expose layers of geological time in the rocks beneath your feet, but those layers are inert. They must be decoded and interpreted. The night sky delivers its layers of time as living light, photons still in motion, actively arriving at this very moment from their points of origin. The past is not merely recorded in the sky. It is arriving continuously as fresh light from ancient sources reaches the present for the first time. A telescope, in this sense, is a time machine, not in the dramatic way that science fiction imagines, where a person steps into a chamber and reappears in a vanished era. A telescope is a time machine in a quieter, more truthful way. It gathers light that has been traveling for unthinkable spans of time, and it translates that light into images. What it reveals is not what the universe looks like right now. It reveals what the universe looked like then, whenever then may be, depending on where the telescope is pointed and how far the light has traveled. The Hubble Space Telescope, during a series of extraordinary observations between 1995 and 2012, pointed its lens at tiny patches of seemingly empty sky and held the shutter open for days at a time. What emerged were images of stunning depth. Thousands of galaxies appeared in each frame, some close enough to show their elegant spiral arms, others so distant they appeared as little more than faint red smudges against the blackness. These images, known collectively as the Hubble Deep Fields, revealed that even in what appears to be the darkest, emptiest corner of the sky, the universe is densely populated with galaxies, each one a vast island of stars. The faintest galaxies in those images were nearly 4 billion times dimmer than what the unaided human eye can detect. Their light had been traveling for over 13 billion years, which means they appear to us as they were when the universe was only a few 100 million years old. They are among the most ancient and distant objects ever observed by any instrument built by any civilization on any world. And yet there they are, small and red and impossibly far away, but present, still glowing, still arriving. And there is light even older than that. The oldest light in the universe is not starlight at all. It is a faint, almost imperceptible glow that fills the entire sky, coming from every direction in equal measure. It is called the cosmic microwave background radiation, and it was released about 380,000 years after the Big Bang, at the moment when the universe had cooled enough for atoms to form and for light to travel freely through space for the first time. Before that moment, the universe was a hot, dense fog of charged particles, opaque to radiation. Light could not travel more than a short distance before being absorbed and re-emitted. Then, quite suddenly on the cosmic timescale, the fog cleared. The universe became transparent, and the light that had been trapped was finally set free. That light has been traveling ever since. For 13.8 billion years, it has been crossing the expanding universe, stretching from its original hot glow into the much cooler microwave range. Today it has a temperature of just 2.7 degrees above absolute zero. It was first detected accidentally in 1965 by two engineers in New Jersey, Arno Penzias and Robert Wilson, who initially mistook it for interference from pigeon droppings on their antenna. What they had actually found was the afterglow of creation itself, the oldest and most distant light that will ever reach us, a snapshot of the universe when it was younger than a human infant and already glowing with the promise of everything that would follow. When astronomers map this ancient light, they find that it is almost perfectly uniform, the same temperature in every direction, with only the tiniest fluctuations, variations of 1 part in 100,000. Those tiny variations are the seeds from which everything grew. The slightly denser regions attracted more matter through gravity, and over billions of years, those regions became galaxies, galaxy clusters, and the vast cosmic web that gives the universe its structure. The light from the cosmic microwave background carries, in its faint and ancient pattern, the blueprint of everything we see around us today. The light year, then, is more than a measurement. It is a bridge between space and time. It tells us that to look outward is to look backward, that the universe is not a photograph, but a mosaic of moments, each one preserved in the light that carries it. the nearest stars show us the recent past. The farthest galaxies show us the ancient past. And in between, arranged in delicate layers like sediment in stone, lie all the ages of the cosmos, still glowing, still arriving, still becoming visible for the first time. Somewhere in the night sky, there is a star whose light left its surface on the day you were born. That light has been traveling ever since, crossing the quiet dark between stars at 300,000 kilometers per second, and it has not yet reached anyone who might notice it. Someday, long after you and everyone you have ever known has lived their full life, that light will arrive at some distant world, carrying within it a tiny fragment of the moment you entered the universe. A record inscribed in photons of a night that mattered to someone. There is a gentleness to this idea that nothing disappears entirely, that light carries the past forward, always moving, always faithful, always crossing the distance between where something happened and where someone might one day see it. Every event that has ever produced light has sent a message outward in every direction at the speed of the universe's only constant, and those messages are still traveling now. The light from the first stars that ever ignited more than 13 billion years ago has been stretched into faint infrared whispers by the expansion of space. It fills the sky in every direction. It is the most ancient light in existence, the last remnant glow of the universe's earliest visible chapter, and it arrives at Earth every moment of every day, unnoticed by most, unheard by all, carrying the memory of a time when everything was new. And the light from our own sun, the light that warmed the Earth today, will continue outward after it passes you. It will cross the orbit of Mars in a few more minutes. It will reach Jupiter in about 40 minutes. It will pass Neptune in roughly 4 hours. And then it will leave the solar system entirely, entering the great silence between stars, where it will travel for years, and then for decades, and then for centuries, growing fainter with every passing moment, but never stopping. Never slowing down. In 4 years, a portion of today's sunlight will reach the vicinity of Proxima Centauri. In 100 years, it will have crossed 100 light-years of space, passing through the neighborhoods of hundreds of stars. In 1,000 years, it will have traversed a volume of space containing tens of thousands of stellar systems. And in 100,000 years, it will have crossed the entire width of the Milky Way galaxy, still moving, still carrying the faintest trace of an ordinary afternoon on Earth when someone paused and looked up and wondered about the sky. Light measures distance in time. It makes the vastness of the universe something we can almost hold in our minds, not by shrinking the distances, but by translating them into a language we already know. Years, the familiar passage of seasons and days and quiet hours, extended outward into the darkness. And so the universe reveals itself slowly, not all at once, not in a single glance, but one photon at a time, 1 year of travel at a time, one ancient message arriving after the longest of journeys. The sky above you is not a ceiling, it is a window, and it opens deeper the longer you look through it. The light is still arriving. It has been arriving for a very long time. And it will continue, quietly and faithfully, long after this night has ended, long after these words have faded into silence. The distances are vast, the light is patient. And somewhere, right now, a photon that left a distant star before the Earth was formed is about to complete its journey. It will arrive in silence. It always does.